Okay. Good morning, everyone, and thank you for coming. What I will talk about today is part of the experience that I had when I was working at IBM. I was with IBM for 15 years, from 1997 until December of 2012. I left in 2012 to take on the position of Dean of the Computer Science and Mathematics and Electrical Engineering at the KAUST University in Saudi Arabia. While at IBM, I was involved in a very large project to build a very powerful supercomputer. We have succeeded in that effort, and I will talk about some of that today. And then I will talk about the research challenges that are ahead of us if we are to take to the next level of performance. So today, the typical high-performance computer, a typical supercomputer, runs somewhere around 10 petaflop, from 10 to 20 petaflop, and it has been the custom in this field to really rate the computer performance based on how many floating point operations it can do. And there is a very famous benchmark called the impact, which has been used to rate these supercomputers. As we have conquered, so to speak, the petaflop barrier, people are now looking at the next barrier in that series, which is the exaflop barrier, something that would be anywhere between 2 to 3 orders of magnitude more powerful in terms of performance than what exists today. So let me start by showing you this picture. This slide actually is not of my doing. This was actually done by some colleagues working at DARPA and working also at MITRE. But I thought it captures the space of HPC applications very well. If you look at the upper part of the screen, we classify the applications in terms of their local node performance on 2 axes. One is the temporal locality, how often or how clustered in terms of time are the accesses to a particular variable. And on another dimension is the spatial locality. If you access an item at location X, what is the likelihood that you're going to be accessing the neighboring data? And this is a useful way to classify applications in general. At the local level, we have effectively 4 extremes, if you will. There is one where everything is nice, you have high spatial locality and high temporal locality, and this is a routine, the DGEM routine, which is a famous one from linear algebra, and it is also the heart of the impact benchmark that is typically used to rate the performance of supercomputers. At this level, or at this extreme here, is the stream benchmark, which really focuses more on the spatial, or testing the spatial locality, and more so the memory bandwidth of the machine. And rounding up the 4 corners are FFT, fast Fourier transform, which is a very challenging application and a very important one in many fields of digital signal processing and other scientific applications. And then at that corner, local random access, when if you think about, if you're doing, for example, research on cryptography, and you're trying to decipher an encrypted message, typically the access patterns of the algorithms that work on doing that are characterized by touching random locations in memory all the time. So there is no relationship between one axis and the next one, either in space or in time. And that type of applications is the most challenging in terms of performance requirement on any given machine today. Most applications written by mainstream programmers and scientists would fall somewhere in the middle of this graph. If you take this local picture here and you map it into a network of systems or a supercomputer connected by an interconnect, you will see that the picture essentially maps in very similar way. We see here FFT remains also one of the challenging applications, and these are the same axes. However, the only difference here is that now the application has a network or a messaging component compared to the sequential version here. HPL is the high performance LIMPAC, which is, as I said, this is really the benchmark that contains this nuclear or this kernel of code. And HPL is really nice. It performs in a convenient way where it shows high performance because of the nice locality of accesses, nice temporal locality, and also it exercises no pressure whatsoever on the interconnect that you have. So it's a very nice application, and it is also the basis or the constituent of the top 500 test, which ranks the top 500 supercomputers in the world. If you go to the supercomputing conference, which is the conference for people who work on that in that area, you will find that there is a session that has been going on now for perhaps more than 20 years, where they sit down and make a new announcement who is the top of the 500 list. And it is the pride and joy of both vendors and national labs and institutions around the world to really be in the top 10, so to speak. So again, the most important thing that I want to take from this figure is, regardless of these extremes, most applications are, somewhere in the center here. They do not really, show very nice temporal locality or spatial locality, except if you have some linear algebra algorithms, which tends to be a little bit in that region here. Now, the reality is, you get what you reward. And if you reward people based on the LIMPAC benchmark, you are going to get machines that are designed to run LIMPAC, which means that these are machines that are not going to really face a whole lot of challenge when it comes to temporal or spatial locality. So if you look at the design space today, it's pretty much most machines, whether at the local level or at the network level, all of them get to be designed and optimized for that region of the space, where the assumption is the programmer is going to do a marvelous job in making the code so nicely structured to increase the spatial and temporal locality of memory accesses. And this is sort of a fantasy, especially when you think that a lot of people who write code for these machines are not computer scientists. They tend to be chemists, physicists, sometimes biologists, who are not really, as far as they are concerned, a do loop is as far as they are willing to consider, in terms of a structure in computer science, and they tend to write these very large functions. And they, by training, they are not computer scientists. They just want to get a result, and therefore, what we have found is that when you look at the real application performance on supercomputers, you may be getting somewhere between 4 to 10% of the rated machine performance for these applications. Like, for example, today we have a 20 petaflop machine at Lawrence Livermore. For real applications that are not tuned for that you may be getting somewhere in the hundreds of teraflop in terms of actual performance, which is a very small portion or a small fraction of the rated performance of the machine. And the challenge that we were faced, and by the way, this challenge has not changed at all since the early 90s, when they moved away from vector machines into clusters of workstations, and then MPI became prevalent. That challenge has been constant, and that style of building machines also has been there since then. The problem of building machines that will be, say here, is that the requirements on the network and the memory bandwidth are going to be very challenging. And in 2001, we started working on a machine that would be designed for this region instead of a machine that is designed for this part of the curve. So I'm freezing for some reason. I apologize for this, I don't know what happened. Working on the actual components of the system that would actually get us somewhere outside this. So typically, if you want to really worry about this part, you want the fastest CPU that you have. If you start moving into this direction locally, you need better memory bandwidth. Likewise, in this figure here, networking or the messaging performance is the critical component for performance on all modern supercomputers today. So what you want is both a network that will equally work for large messages as well as short messages. Today, you will get the advice from whoever designs the supercomputer that you should really try to get as large a message for every transfer as you can. Because with large messages, you amortize a lot of the overhead that comes from preparing the message, running the protocol both in the software and the hardware layers. And what you will find that most of the time, as your applications become more tolerant to sending large messages, the better off the performance is going to be. For shorter messages, however, which is really the holy grail of what the application programmer wants, especially if you're using the messages to do some synchronization, or if you don't have a lot of data that you want to transfer, or more importantly, if you want to make the execution on the CPU to be concurrent with the network so that you don't have to wait until you finish a long chunk of computation and then send the message. You could actually go ahead, as you are computing, you are sending the messages in parallel. A lot of people figured that this would improve the performance tremendously. But for this to happen, your computer has to be able to send these short messages with as minimum latency as possible and with the least overhead that is possible. So the problem is, as you move up in that direction, cost does not cooperate with you. Higher memory bandwidth requires an architecture that has many connections to the CPU, between the memory banks and the CPU, and requires more memory banks so that you could actually exploit the parallelism in memory accesses to your advantage. The problem with that is that it becomes very costly. Likewise, for the messaging, we have learned over the years that to deal with short messages effectively, you really need an interconnect that is designed specifically for that. And that interconnect tends to be also very expensive, and it doesn't help that there are no applications outside of the scientific domain that requires this level of performance. So you don't get to amortize your cost over a large number of users. Instead, whoever is designing supercomputers is going to have to contend with a costly machine that is designed for a specific community of people. Most of the time today, you will see that Linpack machines, because they are really good for just about anything in terms of web serving or any of the commercial applications, they get to amortize the cost in this case. And you will see this notion of how many flops per dollar can I get as the main driver in, as the main driver for how people actually procure machines. And this is really interesting in the sense that if you look at the recent trends of adding performance by incorporating GPUs, for example, graphical processor unit, like the CUDA standard from NVIDIA, or any of the new standards that AMD and Intel is working on. The interesting part about this is that when it comes to Linpack, the machine actually is going to perform very well. And in fact, the Chinese supercomputer that was on top 2 or 3 years ago, it actually used the GPUs quite extensively. The problem is you give this to someone who's going to be writing a real application, and it becomes very difficult to deal with. The code is not portable. It is very difficult to debug. As a matter of fact, because of the limitation on memory bandwidth, people who actually try to port their code onto these newer platforms, they find out that even though you have a bountiful resources for floating point execution, you do not have the ability to move the data quickly enough to these floating point units. So the performance is not really there for the bulk of the application that is, in that range. So what are the fundamental issues? If you look at the design of any computer today, you will find that this picture is more or less the same. This is an abstract way of presenting how computers are being built. Typically, there is a CPU, and behind the CPU there is a memory bank, and then all of them are connected by some form of an interconnect or a bus that takes care of the coherence between accesses and making sure that if you are here and you want to access the data from there, that all of this is going to be done in a very efficient way and without you noticing any kind of difference. And for you as a programmer, you don't really care whether your data item is here or here, and you don't have to worry very much about how you distribute the data among the CPUs. But when it comes to actually executing MPI calls and sending messages over the network, you actually have a very serious issues, because typically you have to go through what we call the I/O bridge, or something like an I/O chip. Behind it, there is all the networking and all the hardware facilities that are required for you to do MPI messaging. So in addition to running the messaging protocol in the CPU, you have the added latency and the overhead of moving data between where the computation actually takes place and where it needs to be prepared, where the messages need to be prepared to be sent elsewhere. Now, this may not be an issue if you're building a general purpose machine that is going to do transactions or any of the applications at the commercial level which can tolerate high latency networking or even low bandwidth networking in some cases. But when it comes to supercomputing applications, that is totally incompatible with the desire to have fast, short messaging between different nodes on the network. And the reason for this is that if you count really the amount of overhead and the time it spends as you go between, to go through these layers, the overhead per short message is so high that it would just kill your performance. And therefore, because of this architecture, they tell you, get your messages to be as large as possible, because whenever we make this crossing here, it's going to cost us a lot in terms of overhead. So you want to amortize that overhead across a large number of bytes per message. So how do we solve this problem? Or how did we go about it? We decided that we want to eliminate the software overhead of running a network protocol on the CPU. Instead, what we wanted to do is to enable the programmer to read and write into remote memory locations as if you were really doing it on a local machine. The only difference is we are not going to make that coherent, meaning that if there is any kind of sharing between different nodes on the systems that are accessing these very remote memory locations, it's up to the programmer to do the right thing, so to speak, because from a hardware perspective, you cannot really scale the network while enforcing coherence. So instead of really sending messages, we are going to be issuing reads and writes. It's just, in this case, the memory is going to be far away. And we designed a programming language to go with this so that the programmer would know from any location whether the item or the variable that you are accessing is going to be local or it's going to be remote. If it is local, you access it like any other way. If it is remote, you have to be careful in understanding how the various components of your applications are going to be accessing these shared remote variables. The other thing that we did here is that instead in this particular picture of having this I/O bridge and all of that wonderful stuff, we put the network directly on the coherence bus. So the network interface actually happens to be sitting here, participating in the memory access protocol as much as any other CPU. So in a way, the network interface that sits here becomes a proxy of the other CPUs all over the network that are talking to me. And it is responsible when it looks at a load request that cannot be satisfied with any of the local memories here because it's a remote address. It will detect this remote address, converts the remote address immediately into a short message that will go over the network with the address of the remote location and the data item in case if we are writing, or it will receive it from a remote location and put it into the local store here. By doing this, we enable some form of messaging based on shared memory reads and writes, eliminating software overhead, eliminating the hardware overhead of going over this bottleneck that tends to really aggravate the latency and reduces the bandwidth. And it enables us to have a very clean design where essentially we're building a large shared memory machine that actually scales to a very large number of systems. In addition to this, if you consider the what we have in terms of the optical and electrical conversion, typically once I am out of the machine, I have to go over an optical network. I mean, copper cannot really sustain the kind of bandwidth and high data rates that are required by modern systems. So I have to convert the electrical signal to an optical signal, and that optical signal will travel to some form of a switch when it gets converted back into electricity, gets routed within the switch so that I could actually send it to the remote location, and again I have to convert from electrical to optical, go on the optical link until I reach my destination. So you look at any kind of transfer, we're talking about 4 conversions from electrical to optical or vice versa, just to send a message from point A to point B in modern systems. Now it turns out that this process of converting from electrical to optical is a very slow process, relatively with respect to the speed of the network and the performance that I'm looking for. We're talking about conversions that could actually be even more than a microsecond, which if you're really killing yourself to get latency sub-microseconds, that actually would kill you. So we wanted to eliminate as many of these conversions as we can, and I will show you how we did that. And I said, as I said, we are going to be bringing this into a new challenge. I mean, we did not envision people who write MPI code that they are going to be changing what they want to do, but they may not get the best performance out of their code on this machine. However, we created a programming language that would enable people to really figure out how to, enable programmers, figure out how to place the data in a way where they understand what is remote, what is shared, what is not shared. And by doing this at the programming language level, you avail the programmer to a new way of writing code. And you have more control over where your data is than, say, what you have today with MPI, where it's not really clear to you what is the right way of placing data, because MPI implicitly requires you to do the data placement, but it doesn't give you really much in terms of programming support for doing that. So if you look at our solution, as I said, we just took an SMP and we decided to scale. Now, within a board or within a drawer, we could actually put all of these, each one of this is essentially a small board with 4 processors on it. That 4 processors are all connected electrically to form a shared memory system. All of these are connected in the form of a full graph to other nodes, and all the accesses within this configuration is coherent. So as far as you are looking at this, you're looking at a 32-way SMP or 32-way processor SMP. And anyone can write to anyone, and the latency is very short, and it's all loads and stores, it's all coherent. It is what you are used to from a sequential consistency type of programming model. Now, if you consider that each one of these is a processor that has 8 cores in it, each one of these cores has 4 hardware threads. This 4-way SMP is in fact it's 4 by 8 by 4 way SMP as far as the logical structure to the program is concerned. So in effect, I have here 128-way SMP in each one of these blocks. And then when you replicate them this way, you get a very powerful SMP, where the shared memory is offering you a lot of latitude in how to structure your local data. Remember, the programmer will have to determine what is local versus what is remote. And it will be a very silly machine where the local is a very small amount of data that doesn't give you the convenience of programming. Instead, what we did is that we made this as large as possible in terms of a single node. So this is the single node, so to speak, and each one of these is going to be connected to the network. Now, in the connection or in choosing the interconnect, we had several options. And these options all were really, at the time when we started working on this project, these were the common options that you will find. And in fact, until today, these are the standard ways of connecting commercial systems. You have a FAT3 switch where, if you're familiar with the InfiniBand standard, for example, that's typically how it is implemented. And typically, you have the machine at the root of the tree, if you will, or at the leaves of the tree, I'm sorry. And then they are connected through some form of a switch that is organized as a FAT3 component. The problem with this approach is that even though it is easy to program, scaling this structure actually has proved to be extremely difficult in terms of cost and in terms of power consumption and performance. The nice thing about it is that it treats all nodes essentially the same, because you could actually say that there is an upper bound that is known on the latency from any point in the network to another. So this is the nice thing about it, and the differential between two neighboring nodes on the tree and two remote ones is essentially log n or sub log n, which is really a nice way of structuring it. But because of cost, and more importantly, because this requires 4 electrical to optical conversions, we decided against going in that direction. The other popular ways of connecting these machines, you could actually look at a switchless torus. So you eliminate the switch and you connect the system in the form of a torus to get that kind of architecture. Or you could actually connect them into some form of a hypercube. And the nice thing about this is that they do not require any kind of optics at all, because each one of these connections is a very short one, so you could actually get by with copper in this particular case. So that tends to be more cost effective. But you give this to a programmer, and it becomes an exercise in geometric modeling in the mind of the programmer on how you're going to be placing the data so that you could actually get any kind of temporal or spatial locality whatsoever. So programming these systems tends to be very, very difficult. And it has not proved itself, or this kind of interconnection has not proved itself except in linear algebra algorithms where essentially it's a near, what they call the nearest near body algorithm. And if you really look at trying to generalize this for a more general purpose applications, it tends to be a very, very difficult exercise. So we decided to do something perhaps a little bit different. So remember, this is really the what we talked about earlier when I showed you the picture of the 4 processors that are connected to one another. And then we get into the 16 of them, or the 16 of them that were effectively connected with a full graph. We decided that the next step is going to be also a full graph that has an optical link between any node in the system and another. And effectively, we have created a network that is 3 levels of fully connected graphs. Now, this puts some limit on the number of systems that we could actually have in this configuration. But remember that each one of these is a very powerful 128-way SMP. So it's a very large SMP to begin with. And when you connect all of these together, the way we connect them, we could actually have up to 256 systems together. Now, you may argue that this is a reasonable number of systems, or you may say, well, this doesn't scale. But I will tell you that in terms of cost, because of the machine was designed really for very high memory bandwidth and short messaging, and we were doing a lot of new things, the cost itself, you would be hard-pressed to actually get maybe 100 of these cabinets hooked up together like that. So at least from that perspective, the scalability part has not proved to be a practical issue at all. So we eliminated the switches, we eliminated the cost and the powers that come with the switches, and we have given also the programmer a 3-level network where the latency between any 2 nodes in the system does not really differ much at the highest level. So if you look at it this way, if I want to talk from any node to another, I'm showing you the flow of information as they are going through the system. The nice thing about this is that, number one, it's very redundant, because if one link is broken, I could actually go and reroute my request through a different link. So the level of redundancy that exists here is very high. The other thing is that if you look at how many link traversals are you going to get there, this is a very simple formula that tells you, what is the probability of one link versus two versus three. And you could see that if you really count this for a very large n, it really more or less is indistinguishable from one another. So you get the picture of a very large SMP across the entire system. And remember, everything that travels into this network is a load or a store request. So fixed packet sizes, very much like a communication interconnect. If you're familiar with the ATM communication networks that is used in telephony today. And you could have a lot of redundancy, as I said, against reliability, or also you have multiple paths that would also help you for congestion. If you have traffic congestion between any two links, the other redundant links could actually be used to offload the communication load so that you could actually improve the performance. Now everything here, as I said, is a load and store, so basically the unit that traverses is a cache line. So whenever you write something, it's essentially an extension of the bus or the memory bus protocol, where all the exchanges are essentially cache lines that are going between various nodes. The only difference is that once I get out of the cabinet here, it's no longer coherent. So I have to really work on adding an extra layer of consistency, and this is where the software actually comes to play. So we built actually this system. It's a part of the Power 7 system at IBM. You could actually see this is really public information by now. And when that core was announced back in 2010, it was effectively the largest processor chip that you can find anywhere. We had 8 cores, 4 hardware threads per core, and an amazing amount of memory bandwidth going off that chip into the CPU, into the memory banks. And of course, the cost was really high, but the reality is that you cannot really get the kind of performance that you're looking for if you're going to be just focusing on mid-time. This is how the whole thing looked like. In terms of the 16 nodes that I showed you before, remember the 4x4 quad? This is how it actually looks. So each one of these is one of these quads. They get to be connected with one another. This is where the optical links. You can see the optical transceivers from this going from the electrical side into the optical network, and then they go there and they start going into the various mainframes in the system. So that's the way it looked. And in terms of a system, this is really one of the cabinets that I was talking to you about. So this is a large SMP, and out of this goes a lot of these optical X wires to other systems that I'm not showing here. And this was the experimental drawer that we pulled out for debugging and so on while we were working on the system. And this is really the picture of the optical interconnect module, if you are interested. This is really the processor quad, and then it comes here and it has the conversions, and then it goes into the various connections in the system depending on where it is actually going. All right, so that was the first half of my talk about what we have built in the past and what we have learned. What we have learned was that you can actually engineer a successful system that would meet the requirements of most realistic applications. And you know, LIMPAC is not really the most desired way of building these supercomputers. In Supercomputing 2012, we demonstrated this machine, and we have shown there was a benchmark called GUBS in Stream and FFT, and our numbers for these benchmarks were way ahead of anybody else in the world. Although from an impact point of view, our system only ran 1 petaflop, so by that time it was looked upon as way, you know, back in the queue because of the focus on the 500 list is only looking at impact. Just to give you an idea, our GUBS number, GUBS is really the benchmark that we were using to measure the performance of short messages. Our performance was in the range of thousands. And just to give you an idea about the next machine, was really in the low hundreds. I mean, we were like 8,000 to 12,000 depending on the configuration. And the next competitor is something like 100 and something. I don't remember what the number was. So the next, the remainder of the talk, I was just trying to really outline the next set of research challenges that are between us and the next level of performance at exascale or exaflop. So, do we really need exaflop? There are a lot of people who say, well, why don't we take a bunch of these petaflop machines and connect them together and be done with them? That is easier said than done, but we have one application, for example, it's a radio telescope or an array telescope that is currently mounted being mounted in the Australian desert to do some interesting studies about the universe and the cosmos. And if you really look at the computation requirement there, it's somewhere between 1.9 to 3.5 exaflops. So this is going to dwarf anything that we have built before. If you look at the data streams that are coming out of this thing, we're talking about 10 petabytes per second. Imagine that. You know, most of the disks today are still measured in terabytes. And just to store this is simply not feasible. This is going to have to be a telescope that actually processes the data as it receives them. And you cannot really afford the style of, I'm going to collect the data, dump it somewhere, and bring it into a supercomputer, and all of that stuff that we do right now. All of these practices are not going to be practical in that era. If you look at also the technology domain or the technology trends, they are not really showing a very friendly picture at all. DRAM is getting faster, but it is extremely power hungry now. In fact, I would say that today, 30% of the power budget in the system are going to the main memory. By 2020, we expect this to rise to about 60%, just to give you an idea what you are going after. The processor frequency will not improve, and therefore we are going to be doing horizontal scaling, meaning adding more and more threads. And if you didn't like having to program 10,000s of threads, be ready for hundreds of thousands of threads, and coming soon millions of threads, which is going to be a very interesting programming challenge. Moore's law, people have been saying that Moore's law is dead, as since before I got my PhD, which was a very long time ago. And it's not dead; it's just going to continue. And we are looking at 7 nanometer now as a practical implementation. A few years back, people say, well, we don't know how to do this, but it's going to happen. But the real problem is that moving data is going to be far more expensive than doing a floating point operation, both in terms of power and in terms of time. So just to give you an idea, this is the number of picojoules that get about tens of picojoules for one floating point operation. To get the data for this floating point unit to execute this operation, you have 2 orders of magnitude more energy that is being spent. And energy is going to be the limiting factor for us. exascale machines are, if they are going to be fitting within the power envelope of a normal data center today, or high-end data center today, this is a huge challenge. We don't really know, because this is going to be scalability by adding more component, which means adding more energy to the energy budget. And in the United States, for example, there is only one national lab that is built next to a nuclear reactor, so that it could actually get all the electricity it needs. I mean, you cannot really afford to do that kind of stuff for everyone. And we are unfortunately going to see a lot more GPUs and SPUs and special use added, because hardware engineers actually are very good at doing that, but it's not clear to us how we are going to be having equivalent improvements in data transfer and data storage to go along with that. So we expect that the programmer's mission is going to get even more difficult. So as I said, we have the power barrier, and at exascale, what we want to do is to get a system that performs at 50 gigaflop per watt. Just to give you an idea, 2 years ago, we were at half gigaflop per watt. Today, we are, I think, 1.5 or something like that. So we still have a factor of 40 or factor of 30 of improvement that we need to do to the system in order to get there. We don't know how to do this. There are tons and tons of PhDs waiting in this this thing in terms of discovery. And the challenge really is to get a system that is used by mere mortals, and not just build a toy limb pack machine and then take it apart, like what happened, for example, three years ago, when a company somewhere built this wonderful limb pack, got into the number one, and then when people tried to use, when the scientists tried to use the machine, it just wasn't working. So this is another open problem that you have here. Just to give you some interesting ideas for research, if you look at the DRAM as it is designed today, it's an extremely inefficient system when it comes to the power, because when you read it, you have to deplete the charge and put it back again. So that's a lot of electricity going back and forth. It's not a lot. We're talking picojoules here, but picojoules, when you multiply them by 10 to the power of 15, they become something serious. When you write, you have to worry about doing the same thing. I found out, interestingly, that these devices actually, if you leave them on their own, they start getting parasitic noise, and whether it is empty or full, it has to be drained every once in a while and written back, which is really what we call the refresh. So there's going to be there is a lot of efficiency here that is out on the table. Like right now, in terms of the efficiency based on n bits, we really computed the efficiency to be much less than 1% in terms of what we get. So that's another thing that people are trying to really work on. The other thing is this notion of 3D stacking. Electrical engineers are fond of 3D stacking because they believe it's going to solve the problem. I did some studies way back, and we showed that you're not solving anything. You're just moving the bottleneck from one place, putting it into another. So basically, you move the bottleneck between the CPU and the main memory into the bottleneck. It's going to be between CPU plus memory into another CPU plus memory. So, and on top of that, you make it even more interesting for the programmer, because now the emphasis on doing very accurate data placement becomes really critical, which is not something that programmers actually are very good at doing. But it might be that this is something that a clever researcher somewhere may actually be able to find a better solution than what has been proposed so far, and make this structure actually work. So that's another, another source of problems to work on. Other architecture features that you need to start thinking about is the notion that we're going to have lots of caches, and maybe the way we're thinking about caches today is not really the best way of building these machines when we get there. For example, the notion of FIFO, first in, first out. A lot of applications actually stream the data into the processor and then stream it out without really maintaining any kind of temporal locality. So for this type of application, the data cache is essentially useless. You're bringing in the data, and soon after you're going to be throwing them away. If you reorganize your data cache more like a FIFO, where basically the data is streamed in, and as soon as it gets out of this FIFO, that's it. It gets written back home. That might be a more efficient way of doing things to really make better use of the silicon that we have instead of throwing it on data caches that are perhaps more appropriate for other applications like commercial applications. Reliability is another problem. I'm not going to get into that, but back to getting back into getting stuck again. Let me. I'm sorry, I didn't cover the reliability part, but I am now doing now at lunch, and I don't want to be on my social. But we have really shown how to build a system in terms of balance between memory, messaging, and CPU. And we demonstrated very excellent performance. Even though our machine is not very rated high in terms of the petaflop, people who actually ran real code on this found that they could get a lot more out of the performance of the machine than a typical supercomputer that is more designed for memory. These two problems, along with scalability for going to the exascale, is really the next frontier, and actually has plenty of problems to work on. So this is really the scope of research that you could actually see. There is a lot of work, whether it is compiler, or programming models, or statistical machine learning, so that you could actually improve reliability, exploitation of new hardware in smarter ways. There is this whole notion of stable semiconductor memory and what does it do to you. So far, we haven't actually found out a good way of using them or using these devices. You will need some form of virtualization to improve your reliability, and you need to be better at the failure detection and so on. And with this, I'm just here expressing my gratitude for my colleagues. At some point, 200 people plus were working on this project, and I was actually less than cursed to be the leader. And without them, actually, none of this would have happened. But of course, this has not been vetted or approved by any entity, and so all of this is fictional and has nothing to do with reality. Right. Thank you.
Do a little bit in reverse. Normally we introduce the speaker first and then he talks. Well, we let him first talk. It was on purpose. Believe it or not, he's a dean. He's the dean of engineering at King Abdullah University in Saudi Arabia near Jeddah. And he, going backwards in his past before becoming dean, which is a relatively recent event, he was at IBM for 15 years. He was a second line manager, kind of more like a director level of manager in Austin Research Lab, so it's not very far from here. And from there, he directed PERCS, which was a DARPA program. That is actually what he was talking about today. And it was actually quite successful and quite unique project. I had actually some intimate knowledge about it at some point, working a little bit on the same thing. And then before that, he graduated from various fine schools, beginning with Cairo University, and then MS and PhD from Rice University, also around here. Went to Carnegie Mellon and was there a professor for a few years. Got even a career award in the process. Decided it's not for him and went to IBM. He is best known, or well, I shouldn't say best known, but he's certainly known for his contributions to fault-tolerant computing, to fault tolerance. His paper, his seminar paper, is actually becoming more of a textbook paper nowadays. So if you didn't read it, I suggest you do. So now we would like to, on his behalf, I will accept questions for about this. Go ahead.
I have a question. So you mentioned that the routing was kind of dynamically or adaptively adjusted based on, traffic. How was that done?
Are you talking about the algorithm itself?
Or just kind of, at least at a high level?
Basically, it is, there is a feedback mechanism that tells you when the data that you sent arrived on the other side. And when that feedback mechanism shows the considerably increasing delay in getting that feedback, we conclude that something is going on that link, whether it's a failure or an overload, and we start distributing the workload across different other passes based on a static algorithm.
So it's basically kind of a local adjustment based on delay.
On perceived delays.
I have a couple of questions, somewhat different. The first one is, comment on the ease or difficulty of debugging software that you run in some systems. And the second one is, there has been work, but is it being considered again as to make memory more intelligent, so a lot of work to memory elements as opposed to maybe to the CPU to the computation?
Okay, so the first question really had to do with the difficulty of debugging software on the system. I claim no advantage whatsoever in terms of helping programmers debug code in any way that is better than, say, existing MPI systems. The problem of debugging is a fundamental one, and very little work actually has gone on, or maybe I should say, there's a lot of work that has gone on into this area, but the results in terms of things that are available to real users hasn't been there. I mean, there is a lot of people who are still doing printf to do their own debugging. The second part of the question is, why bring the data from memory when you could actually move the CPU into the main memory itself? This is essentially the idea of putting these 3D stacks where the CPU gets stacked with the main memory, becomes part of the main memory module. And it's nice in the sense that it removes the bottleneck between the CPU and the main memory, but it moves if Amdahl's law still is there. So we move the bottleneck from the point between the CPU and the memory into the link between these components, next to each other. So when you do a really performance assessment of this, you find that it's not really, you don't really gain that much. On top of that, you are now at a level where you have to worry about which part of your data is in which memory bank. So we move into a level of complexity where the interleaving of memory all of a sudden becomes apparent to the programmer. And there is a lot of debate about whether this is a good idea.
I see that there are so many ways that getting access to systems is possible. But the bottleneck seems to be how to hide this complexity from the programmer. And it seems that the programmer is the bottleneck. Do you think that maybe there is a place for the future to develop developers that are able to handle this level of complexity? To program high speed.
So the question is really about the programmer actually given that it has been difficult to program these systems. The question argues really that the bottleneck is really the programmer. If we had better programmers, perhaps they could actually make better use of the hardware that exists today. That argument has been going on for a very long time. And those superhero programmers exist, but there are very few of them. And in order for you to really democratize, if you will, access to these machines among the large group of scientists who are not computer scientists has been really an elusive target. Nobody has figured out how to do it.
It's an issue of training.
It's an issue of training, but if we're going to say it's an issue of training, then we are condemning all the computer science departments that exist already throughout the world. And I don't think this is a reasonable thing. We have to realize that programming these systems is very difficult by its nature, and our brains perhaps think in different ways than what the von Neumann model has. So there are lots of people, for example, now in Europe and in the United States as well, who are really looking for a completely different model of computing, where let's go and mimic the brain. And maybe in 10, 20 years, we're going to get some systems that by learning, they could actually, I don't want to say program themselves, but at least go in a certain way in optimizing their own execution, optimizing their own data placement and things like that. We will see. I mean, that's another area of research that is wide open. Nobody has managed to figure out how to solve. All right, thank you so much again, and I appreciate the opportunity to come here and talk. And this is my 6th visit to Texas A&M. It's been always a pleasure to come here and meet with the faculty. And, I am really impressed that every time I come, I see a big delta of improvement in every aspect. And maybe people who are here do not notice that because they are continuously here over time. But it's definitely I see a lot of excitement and a lot of improvement over my last sample. So I think you should be glad and proud to be in this place. I'd really like to thank